Welcome to today's Accendo Reliability webinar series session, and this is Fred Schenkelberg. And today I want to talk about formulas. And years ago, when I was working at Hewlett-Packard, Dick Moss said, and we were in a conversation, and we would often go for a walk at lunchtime, and I enjoyed so much with talking to him, and it was about day-to-day activities or long-term paths for the career of reliability, how to influence cultures. We talked about all kinds of things. And I asked him one time, what does it take to be a good reliability engineer? And he thought for a second, he says, well, there's all kinds of different things, but you also need to know the math. You need to do the roll up your sleeves and use the range of formulas and use them correctly. And I said, well, there's so many formulas. He goes, in reality, you only need 5 formulas. And he rattled off a couple of them real quick. And I said, well, that was only 4. I was kind of keeping track of these and trying to make mental notes of which ones I needed to keep track of. And he said, well, the 5th one is the one that you need to solve the problem in front of you. And I think that's the gist of the today's discussion, is that, yeah, there's a lot of math out there, but you have to keep in mind, as we've talked about on so many different webinars, that it's got to be to add value. You're using the formula not just to show off your integration skills, but it's to solve a problem, to inform a decision, to estimate a sample size for budgeting, and we'll talk about a handful of different concepts. But as I look through all the various formulas and all the different things that we get involved in, and all the kinds of tools that we have available, I found that there was about 6 different ones that characterize different types of math that we need to be able to master. And I think more importantly is the concept of those types of approaches, of why these formulas exist. Now, part of every formula, and I even got a question, I think late last week on LinkedIn, that said, why is it that 85 Celsius and 85 relative humidity is in so many different testing standards? Is there something magical about 85? And well, no. I even ran into years ago a standard proposal that was going to expose bare silicon die to temperature and humidity, and the humidity would immediately corrode the surface of this chip, and of course it's going to fail. That's why we encapsulate them. That's why we put protective layers on them to keep the moisture away from it so that it doesn't corrode. And the proposal folks in the standards body were serious that they wanted to expose bare die to these conditions without coatings on it. And it's like, well, what's the point? It's going to fail. And the idea of the limitations here is with these different formulas is that, especially when it comes to testing and understanding the testing results that we get, is those things almost always are related to a particular failure mechanism. And that's just one example. Well, I don't want to tip my hand on all the different limitations that we'll talk about, but that's something to always keep in mind, is that if I'm looking at a formula, is it appropriate for what I'm trying to work on or what I'm doing, right? Now, that the other piece of this is that almost every formula and every equation that we deal with has underlying assumptions. Simple things like, well, let's assume it's a constant hazard rate. And you all know what I think about that assumption. But the idea is that we make explicit assumptions deliberately to simplify a problem, to create a model that we can use to move forward our understanding. But we also have assumptions that are built into the original derivation or use of the equation that we're dealing with. And so being aware of those and in checking those assumptions is a critical step in using any of these equations that we use that cross our desk in one form or another. So that's my intro. That's what I'm going to talk about. I'm going to dive into 6 different formulas that are characteristic of 6 different types of things that we use. And these are just ones that came top of head, top of mind to me, and so that's why I picked those. There's nothing particularly, I don't know, earth-shaking about why I picked these particular formulas, but they're examples of classes of formulas that we need to understand and be able to use. So the questions tab is available to you to interact with me, and I'll keep an eye on that as we go through. But what's your favorite formula? What's your go-to formula, or one that comes immediately to mind when you're thinking about formulas that we use? This gives me a chance to get a sip of water before we dive into the first one. I don't know. One thing you could do is just write down what your 6 formulas would be, what are characteristic or formulas that we should have a good understanding of, and then compare those to what I have. And I will have some time through this session to say, well, that's not the right formula, or this one's more important, that kind of thing. Zubin, the Arrhenius equation, not my favorite. Let me see what else you got in there. Yeah, it's out there. You see it a lot. It is useful. There's no doubt about it. Let's see, Weibull. Yeah, I figured that one would show up. Weibull in our business is kind of the normal of the normal world. Power law. Yes, that's a good one. I didn't think of that one. All right, now you're just playing with me with the exponential distribution. If you're going to sit for the CRE exam, you need to know the exponential and the chi-squared, but beyond that, I wouldn't use it in real life. That's a subject for many other ones. Conditional probabilities. Yeah, I like that. That's a good one, Sivastan. I think I'm pronouncing your name right. I'm sorry. Chi-squared inverse, Zubin. Good, good. All right. Yeah, we got a few people that are doing stuff. I'm going to try to broaden that list a little bit. You hit a couple of them that I'm interested in, and a couple that I don't want to talk about, because I'll get into the no MTBF type stuff. That's one I didn't think of, redundancy equations or modeling. But I think I get, that's a good one. I didn't think of that one. All right. So one of the formulas I want to talk about is Bayes' theorem. Now, this may sound odd coming from somebody that's a frequentist. I went to Stanford University for my statistics area, and availability, yep, that's a good formula. And there's a lot of, I think many of the concepts we're going to talk about today will tie into this. But Bayes' theorem is a foundation for Bayesian statistics, but it's also really, really useful for conditional probabilities. And we use those all the time. We know something and then we're going to move forward to it. And so the formula itself is actually pretty simple. But the idea here is that it's a theorem or a rule or a formula. It's got a bunch of different names, and it's looking at, well, how do I incorporate information that I have in order to better inform what I'm interested in calculating? So I'm going to calculate the probability of A happening, and this is using set theory, the event A, and I know something about event B. B has already occurred. And for example, the example I always use or think of is that, what's the probability of rain today? And I look outside and I inform my decision by going, oh, it's cloudy and it looks like rain clouds. And the weather forecaster forecasts a high chance of rain today. I could use that information to inform my assessment of the probability of rain today. Whereas where I'm at today, it's bright blue sunny skies, and actually we don't have any or much smoke in the air as we've had over the last couple months or the last month. So it actually is a nice bright blue sky. So my assessment of the chance of rain is informed by this bright blue sky, saying it's very unlikely that we're going to have, I don't think it's going to rain today. Now, part of this is based on the idea that we know some of these conditional probabilities are in the individual probabilities, and you can rearrange this formula to calculate all kinds of one of these four elements that are in it, knowing the other three. But the underlying concept here is that we're able to incorporate information into a, informing or altering our probability calculations for some activity or event or probability. And there's a lot of thought process and rules and things like that go into it. And Chris Jackson did a really nice webinar a couple months ago on dealing with incorporating information into it. And he was talking about Bayesian statistics in the concept in much more detail than I'll go in today. Now, the place I run into Bayes' theorem almost all the time is in checking an assumption that the events that I'm using in my test, for example, or the products that are out in the field and failing, or the equipment as it's being operated, is that the events that are occurring are independent. You know, the stamper on line A versus the stamper on line B in my factory, if one fails, the other one is not automatically going to fail. It's not influenced or somehow connected or knows that the other one failed. Now, they might both just wear out, but I'm making the assumption that they're independent. Now, that might not always be true. If line A is down, then line B might double its throughput, and it increases the chance of it failing. But that is in that gray area, and statistically, we can test that, and Bayes is one way to go about doing that. And so it comes in handy in checking assumptions in my mind, but its primary purpose is to incorporate information that we have and account for that. Now, some of the issues I have with it is that you need to have a lot of information. You need to have counts and data and information about these different things. And Chris's webinar talked a lot about, well, you can even use expert theorem or expert opinions, or you can use the power of the crowd to incorporate a large number of inputs in order to get that best estimate or best input to it. And it's pretty powerful in that way. And there's lots of reasons why that works. But one of the limitations is that, you know, instead of looking out the window and saying, oh, it's clear today, it's not going to rain, I could look out the window today and saying, well, it hasn't rained for 6 weeks, so I expect it to rain. Or I could look at the almanac saying, well, on this day in history, we usually get rain. And some of those may or may not be related to the actual phenomena that creates the probability of rain, right? So there's the famous one where a particular baseball league wins the World Series baseball tournament, then the stock market will go up or down. Now, just because there's an apparent relationship between two things, there may not be causation. And Bayes' theorem in the formula itself doesn't know whether there's causation or not. It's just looking at the probabilities. And if you check enough different sets of data, they may line up in just by random chance. And that's a danger of it, is you can find things that look like they're influencing things, but they really don't. And so it's one of the limitations here is you still need to think through what's actually happening in the real world. And also one of the limitations is are you accounting for all the things you should be counting in these probabilities? You know, if you're dealing with a deck of cards, it's you know the deck. We know we can evaluate all the cards. We know how many kings there are, how many number twos there are, and so on, which suits there are. We can count all of the variations of those things. And it can be tedious, but we can do that. Now, in some cases, like when we're in production and we're constantly adding more units to the field, well, then where do we count? What do we not count? If units are retiring from field or put in stores and not put in service, which ones do we count as active or not active? How do we do that? So some of those probabilities get a little muddy. And you see a comment here from Silverstein. Yeah, it's part of the MCMC, I think it was his first one that he talked about, um, the power of previous information, of group information. And with right now my screen is in present mode, so I'm not able to find it, but I think it was his first one like 2-3 months ago on the MCMC topic. Okay, now some of the assumptions here is that the probability of A and probability of B are not zero, right? And it goes into that dividing by zero issue. And it's obvious that we're dividing by probability of B here, but you can rearrange this formula a number of different ways. And these conditional probabilities are also dividing by the individual probabilities. So even if the hard part is that, well, if it's very, very small, it's virtually zero, but to avoid the mathematical problems, we don't say it's zero. Now, the other part of this is that there's a finite chance for the events we're dealing with actually do occur. And so we need to understand those things in the joint probabilities. Another one that I read about just the other day, and I didn't really dawn on me, is that it's also implying that the probability A given B implies that there's a probability of B is influenced by A occurring. And if they're sequential, that's hard to understand how that occurs. But it doesn't, in the formula itself, it doesn't have that time constraint. And so just because B influences A doesn't mean that A influences B, but it seems to be built into the formula. And I thought that was interesting and worth exploring a little more. And the other part I need to stress is that the assumption is that A and B are the only ones in the game. What if there's some other factor, some other influence that affects whether or not there's a relationship between A and B? And so thinking through, do I have a complete picture here? Is my model adequate for what I'm doing or not? And that's an assumption that oftentimes gets overlooked. You know, rain clouds and rain, okay, I can deal with that. Although I was on a freeway in Texas one time and bright blue sky and it started raining. I thought like a water main had broke or something like that. And they said, no, it was actually a rain cloud that was over the horizon, but the winds were so strong that day in the upper atmosphere, it blew all the water over. And so you don't always need clouds to have rain, is what I found in Texas. All right, so I'm going to shift to another one. And Bayes' formula is I should wrap up Bayes' formula. The concept is it's a realm of understanding how do we use information, and then also how do we check assumptions. And so it's a pretty useful tool in that realm. Now, let me shift over, and let's say we're dealing with pass-fail data. What formula or equation comes to mind right away with that? All right, hopefully you're thinking binomial distribution. It's the distribution for count data, essentially. Oftentimes we just deal with a pass-fail or Bernoulli trials where we have a finite probability of pass or a fail. And the easiest example we all learned in school was flipping a coin, a fair coin where it's 50% chance of getting heads and 50% chance of getting tails. And the idea here is that the formula allows us to deal with this kind of data, pass-fail data. And it doesn't have to be fair. It doesn't have to be a 50-50. It could be an unfair coin that's heads 25% of the time. Now, one of the things I learned early on, because I often got it wrong in math classes, was that you have to be specific about what do you define as a pass, right? So, or as a success. And so if I want exactly K successes in N independent measurements, for example, or experiments, and I define product failure as a success, and I want to know how many failures are likely to occur, and I know the failure rate, which would go into the P, the probability piece there, and I have 100 units, well, how many failures should I expect? And I could run out this calculation and I would expect exactly 3 out of 100 units if my failure rate is 3%. And that's not too terribly difficult. It gets a little tedious, and there are shortcuts and variations for using binomial distributions for the cumulative distribution and things like that, and even approximations using normal distribution of, well, how likely is it that I'll have up to 3% failures? So I'll have 0, 1, 2, or 3. I always cringe when I see those kinds of questions on an exam, because they are kind of tedious to do with this basic formula. So you need to know how to deal with the cumulative ones or do some other tricks mathematically to get to the same point. Now, the distribution has I think, a downside, and it allows us to do success testing. The formula for the samples, how many samples do I need to run a test under some conditions, and shows that it has some minimum amount of reliability, the lower level of reliability. And it uses the binomial, and it can be derived a number of different ways, but binomial is one way to do it, where I'm looking for exactly 0 failures, or as we define them, successes. And then I solve for, well, how many samples do I need to run through that situation? And I call it success testing, because that's exactly what we're trying to do. Is we're going to say, if I run it under, say, 85 for 100 hours and I get no failures, then it's at least 80% reliable with some confidence, as an example. I think that's efficient. It allows us to do a lot of cool things. It allows us to set up testings with the minimum number of samples being involved, all kinds of cool stuff. It allows us to deal with pass-fail data. But what it relies on, though, is that it's discrete data, right? It's pass-fail, or it's red, yellow, blue, or whatever types of data we're dealing with, but it's discrete data, count data. And many of our tests, we don't learn a whole lot when there's no failures, right? We don't know if the test was actually accelerating or invoking the failure mechanisms that would occur in normal situations. Was it even hooked up right? Or was measurement error a fault of this so that we miss things and we didn't see them? By running to failure, we get the failure itself to do the analysis to understand, well, what failed and why. And it allows us to do time to failure data, the continuous data set, which is way more powerful, more informative than discrete data. Now, sometimes that's all we get is pass fails. And so dealing with it is the domain or the realm of binomial distribution and its related discrete data handling. So it is pretty useful. One of the other limitations of it is that each sample in the testing, for example, will pass or fail completely independent. It's like separate coins, or each flip of the coin is not informed by other ones. So things like common cause failures, they were all made by the same day in production, the same batch, the same vendor components, things like that, may lead to common cause failures that destroys the independence. And that's a hard one to check as an assumption and to design away from. Now, some of them, one of the assumptions that's a little harder to get away from when using the binomial is that the probability is constant. What if every time you flip the coin, it changed its probability slightly? So it started out 50-50, but after 100 flips, it was 49-51, and so on. What happens when the probabilities are changing enough that it will change the results of your experiment or the analysis you're doing? And I'm using a really simple example there. The other part is there's this understanding that we're doing random sampling, and this is implying that we have every item that's under evaluation has an equal chance of being included, because almost always we're dealing with samples, and the sample then is representative of the population. Now this gets really dicey when we're in prototyping, right? Because the population we want to know about is future production. And so let's say we make 1 million inkjet printers over the next year. but we're only sampling 20 that we're making today. So all million units do not have an equal opportunity to become part of the sample. And so sometimes we waive that random sampling just out of necessity, because we're not going to make all million of them and then do our testing. So, but that starts to erode the ability of these distributions, and not just binomial. Anytime we're doing random sampling, or taking a sample to represent a population, it erodes the ability to project what the population is doing. And so we need to guard against that when we can, and understand the risk when we can't, right? And also that we're assuming, and we'll see this over and over again, is that the measurement error is really small. Okay, let's switch over to comparisons. And I suspect you're thinking of hypothesis testing, maybe bar charts. It's another way to do it. But, well, confidence intervals can allow you to make comparisons, but, and there seems to be the same data and almost the same types of statistics as doing a hypothesis test, but I'm going to dive in hypothesis testing. It's a whole nother realm of formulas that we use, and they allow us to compare things, compare to a standard or a fixed value like a specification. Are we in spec or not in spec, and how do we know? And then is vendor A or vendor B better at some aspect of our product, some performance or characteristic or lifetime or whatever? We can compare things and get an idea based on samples and some measurements whether we've made a significant enough difference or not. And so part of this is we can compare things, and we can evaluate items from a sample and project out to what the population should be performing like. And we can compare means, we can compare variances, we can compare pretty much anything you can think of. There's formulas for all kinds of different ways to do this. The comparison of means using the z-table, the z-test as it's called, it requires we know the population variances, which we almost never do. So we often use, and it's in really small font, and sorry about that, is the t-test. And that illustrates that if you don't really know the population variance, then you're using the sample that you're gathering to estimate it. And so that's contingent on the sample size. And up until about 25, 30 samples, there's a difference. And then we use the t-test. But that's just one of many considerations in picking out the appropriate formula to set up your comparison. And if you have discrete data, if you have count data, if you have, if an item can fail only one way, or can it fail or have multiple things. Think of a car door where it's has a dimension is wrong. It either is right or it's wrong. It's in spec or it's not. And it's one way it can fail. Or it has paint blemishes. It can have one paint blemish. It can have 20 paint blemishes. So it could have 20 items that show indications of failure. So you can have an item that when it fails, it counts as one, or if an item fails, it may count as 20. It goes into different formulas. Are we doing paired comparisons? Are we doing, do we know the variance? Do we not know the variance? There's dozens and dozens of different hypothesis tests, not to mention all the non-parametric ways to do comparisons. So part of the problem with hypothesis testing, and when we want to make a comparison, is, well, which one? Which one do we need to do? And so it also has these ideas of random sampling and measurement error and all those kinds of things come into play. We need to set up an appropriate experiment. And one of the things to wrap your head around is you have to be careful about, well, what do you set up as the null hypothesis, and what's the alternate hypothesis? And the general guide is the null hypothesis is, for example, there's no difference. And I'm trying to detect, is there a difference? So it's in your intent how you set this up. So I want to create an alternate hypothesis that I want the data that if there is actually a difference, for example, then the alternate hypothesis will bear witness or evidence that there really is a difference. That's what we're trying to evaluate. Now, where I got tripped up on this, it was a limitation. It was I was changing a process. I was bringing a system online or a process online, and I wanted it to be similar to the existing process. So instead of being different, I wanted to show that it was the same. And so I had to reverse my thinking about the null hypothesis and alternate. The null hypothesis was that they were different. And the alternate hypothesis, which I wanted to gather evidence for, was that they're the same. In all the textbooks show these the opposite way, is A equals B is the null always, and A does not equal B is the alternate, is in every textbook. But that wasn't my intent. I wanted to gather evidence that way. And so one of the limitations is that if your data set shows that there's not, the alternate hypothesis doesn't have sufficient evidence to show that it's really true, it does not mean that the null hypothesis is true. And I was trying to get my tablet here to be able to draw on this thing. That's one thing I haven't sorted out here. But the idea, let's say you're comparing two vendors and you're making the assumption that they're the same, but you want vendor B, which costs a little more because it may add some performance or lower yield or whatever the characteristic is that's desirable, but you want to gather evidence that it's worth it, that there really is a difference. The point is that if I gather evidence and there's a huge difference and I have convincing evidence that the alternate is true, I will then justify the higher price and use the new vendor. On the contrary, though, if the data isn't convincing, I don't have enough evidence to say, yes, the alternate hypothesis is true, it does not mean they're equal. It still could really actually be different and better, but the particular test we did was insufficient to detect that difference. That's all it means. And so being careful about how you set up the null and the alternate you have to wrap your head around about what evidence are you trying to convince yourself is actually true, and then use the setup of the example to do it. So it's one that took me, and I got it wrong a number of different times and made that erroneous conclusion that if the null hypothesis was not disproved, doesn't mean it's true. And that was always hard for me to understand. But it's one thing to keep in mind. Now, a couple of different assumptions that are on here is oftentimes it's underlying that the sample mean, the sampling that we do, the means of those things, if we took many samples, that those things would follow a normal distribution. And that oftentimes invokes the central limit theorem. So that's usually not too bad. But in some cases, we need a pretty large sample in order for that to become meaningful. Fortunately, central limit theorem is pretty powerful. So samples of 5 to 10 are oftentimes take even really weird looking underlying distributions, and the sample means will come out relatively normally looking. Now, sometimes though, and this is one that I rarely ever tested because I almost never had enough data to test it, is that the variances of the two sets of samples I'm gathering, if I'm comparing two things, were identical. The variances themselves were from normal distributions. And that's not always true, and they would be the same. And especially when I'm checking two different vendors, if the variances are not the same, the underlying variance of the population are not the same, well, then you need a different formula that accounts for those differences in variances. And in some cases, if it's $1 million decision, well, let's go test the variances to see if they're independent and equivalent to each other. So it's one of those assumptions that in important situations, you should really go off and take a look at. And then these independent things, well, that goes back to Bayes' theorem. That's one way that we can test for independence. So hypothesis testing is something we learned early on in our stats classes. It's a very powerful tool, but Yeah, but you can get it wrong lots of different ways and still think you got the right calculation. So it's one of those to pay attention to and understand the underlying elements of it so that you set up and design the test appropriately so that when you do get results, they're meaningful. And that's important to keep in mind. And that's true with all these formulas, is understand them. All right, I'm going to shift now to uh, capability. And again, here you should probably immediately think of something like control charts and XBAR and S charts and process capability studies and things like that. These have been around. Process capability and SPC has been around for over 100 years. And there's lots of interesting ways to go about doing this, lots of ways to do control charts and so on. But one of the issues that's important to keep in mind is that process capability is not just to improve yield on your production line. It's a great way to do that. But it informs how do we set tolerances on the design. So if you've got a metal stamping process, it will have some amount of variability and just inherent in that equipment. And it might wear as the dies wear, it may change the dimensions of the stamped components. And in some facilities and practices, it's you change the drill bit after 1,000 drills or 100 cuts or whatever it is. And because they know that it's dulling and it's not cutting as cleanly and holding the tolerances correctly. Well, I have found that a reliability process is important because if I specify plus or minus 2 mils on a design, but the process that we're using is only able to keep within 6 mils, then a good amount of our products are probably not going to be in specification. And if that's important for the reliable performance of the product, well, then we got a reliability problem. So informing the ability to design by understanding the manufacturing process, the assembly processes, our vendors' processes, is critically important. And so that's how I connect it to reliability. If there's variation in our components, even if they're just on the edge of our tolerances, the product is not going to perform as well as it should. Many of you know that I was a manufacturing engineer initially, and so I always blamed failures on the design because they weren't taking into account the amount of variability that we were adding in the manufacturing process because we weren't going to make it better. We were going to add chaos to their product. That's just what we do. And because that's the real world. And the idea here is with process capability is that it allows us to understand and monitor processes and compare them to the specifications or tolerances. And it has a number of other purposes too, but from a reliability point of view, it's really, are we able to hit our specifications? And or do we have the right specifications given the variability that's to be expected in this process? And I see a comment here is that if it was just CPK, it would be nice. But there's PPK and there's PMK. There's whether the tolerances are centered or not. There's like hypothesis tests and like the discrete distributions. There's all kinds of them, right? And selecting the capability is part of that process. And hopefully everybody here understands that the CP, C sub P, the process capability, and it doesn't account for centering. So you could have 100% yield loss and still have a high CP value. It just happens to be centered outside your specification, but its width is well within the range of the specification, but it doesn't line them up. So most of us know to use CPK or similar ones because it takes into account is the process within the specifications or not. And so that helps us deal with that. But the idea here, though, is one of the limitations is that the process that we're getting this process capability information from first has to be stable, and that's the control charts, right? We need evidence that the process is running consistently. And part of that is that we know it's going to shift and change. And there's a normal amount of variability in every process. But is that range of normal, and I shouldn't use normal, expected variability, say seasonally or by batch to batch variation, or as tool wears and gets reset, is that amount of variability altogether consistent and stable? Then, and really only then we should calculate CPK or its similar types of values. The hard part is that you can get a CPK value, you could specify CPK values, and you might get just a number back. Oh, we're at 2.6. Well, that's meaningless unless there's evidence that the process is stable. So one of the limitations is that it takes work to get a process stable. And the other piece is that for critical processes, things that are important to the performance of your product, is keep in mind that these things change, right? They might get better, which is great, or they might get worse. And you've heard it as many times as I have, is the vendor says, well, we're moving to a new building. It shouldn't affect, we're going to use the same people and same equipment, but their variability goes through the roof. And so their process capability gets reduced significantly. Or they're saying, oh, we're making a change, but you shouldn't see any effect of that. Well, I always raise an eyebrow with that because I've heard that so many different times. And sometimes it's true. We never notice and it's no big deal. But on occasion, when it says, why did you change the process? It's, well, we didn't think you'd notice. It's like, well, yeah, we did, kind of thing. And so the idea here is that process capability is not a one-time shot, but it is immensely useful for informing setting specifications and tolerances. Now, another piece of this is there's a pile of assumptions in there, and I probably already talked about all of these things. But one of them that I find very rarely assessed is the measurement system stable? It's not only that it's capable of making the measurement, that you do the measurement system analysis for your measurement system, is the measurement error relatively small compared to what you're trying to detect, but is it stable? Is it consistent? Is temperature through the day or through the seasons, does that affect it? Does it wear out? It's more complex than just calibration. Is it stable? And so it's those elements of the measurement system analysis that look at it over time. So things like, is it drifting, for example? And so those are parts of the assumptions that are involved. And I think SPC and process capabilities is one of those exceedingly powerful tools for reliability and for our design for reliability aspects. So that's why I know I purposely put this in there, because I know it's so critical to our reliability stuff. But many of us hand it off to the manufacturer or the quality engineering teams, where they're looking at yield and throughput, which are good things to use these tools for, but it's not the same as then measuring things that affect the reliability performance of your product and the setting of appropriate tolerances. So those are ways I would do it. Right now, when I first started, I asked about your favorite distributions, and there was Weibull was right in there. I think Arrhenius, which is my next and last formula, is a piece of that also. Weibull distribution is such a flexible distribution. It can model all kinds of different things, from the exponential distribution when beta equals 1 to a normal-ish looking one. I think it's at beta of like 3.5 or 3.7, something like that. Here's a quick quiz for you. Anybody know what the beta value is of a Weibull distribution when it's called a Rayleigh distribution? I always think of Sir Walter Raleigh. That's quick, Michael. You knew I was going to ask that too. A couple of you are getting that. Good. It's one of those little fun things that if you end up with a Weibull with a beta of 2, you can say, oh, we have a Raleigh distribution, and I'm sure that'll impress everybody at your next barbecue. Other than that, I don't know why it has its own name. It has some nice characteristics and features to it, but it's just, yeah, somebody got their name on it. Weibull distribution is pretty powerful. We use it for all kinds of things. I use it, to be quite honest with you, is I get a set of life data, I drop it into a Weibull distribution. It may not be the right distribution, it may not do me anything, but it gives me a visual to give me an idea of what the data looks like, right? I might do a histogram, which is similar. I could maybe fit a Weibull PDF to it, but I don't really need to. I could do a histogram, I get a visual of it. And sometimes I'll do a dot chart to see where things are, especially if I have complete data. But I always put it in a Weibull. And if for nothing else, I can say, oh, this is an increasing or a decreasing failure rate. Now, that's not always true if the Weibull really doesn't fit your data, right? But it's one way to check real quick, but plot the data, draw the line through it, get a sense of, is this reasonable or not? Oftentimes our data sets are small, and so differences between the Weibull and log normal distribution are very hard to detect. I tend to drift to the Weibull because the beta is informative in and of itself. But that's a slight preference to Weibull, and it's just habit to a large degree why I start with Weibull. But then I start questioning that. Do I have the right distribution here? Is fitting a distribution appropriate? You know, if it's bimodal, if I have two peaks in the data set from my histogram, well, then Weibull and log normal and all these other ones really probably don't apply. Might be a joint distribution of two different things, or I better just stay with nonparametrics to do the analysis if I really don't understand what's going on here. So like all the other ones, the Weibull distribution or log normal or the nonparametric models are a way for us to describe failure data, to model it, to get an estimates of failure rates or probability of onset of the first percentile of failure, what's the nature or pattern of the failure rates over time, and we can project into the future. So these models and the analysis of time to failure data allow us to do a lot of interesting things and support a lot of different kinds of decisions. Now, of course, there's limitations, right? They're a model. They're just a representation, a line through a set of data. And regression analysis does a lot of cool things to help us get it right, but it's not perfect. It doesn't account for all the phenomena in physics and all the different failure mechanisms at play. If there's a failure mechanism that occurs only after 13 months of performance and all of our data is only been aged for 12 months, where our model is going to be wrong. We just don't know. We don't have the appropriate data. Another limitation is at system level, when you're doing a repaired system like your vehicle or a process, an asset in a processing plant. If it's a repairable item, then we need to use other types of modeling in order to understand it. But within that system, if we're looking at just motors and similar motors, then the Weibull distribution may be appropriate if we treat it as non-repairable, even though motors oftentimes are repairable. And so there's, like hypothesis testing, like control charting, you need to apply the appropriate model, which is really one of the first limitations, and I should have listed it first. But it does have a lot of cool benefits for us to do our job. So I tend to use it quite a bit. So question, Srivasten, is what's the best distribution to deal with quality failures? Is non-parametric like Kaplan-Meier an option? Well, Kaplan-Meier deals with time to failure data, right? We have failures out over time. It's not necessary, and I don't really know what the difference is between quality failure and reliability failure. Now, if I'm in a factory and I have a yield loss and I created a product and it's out of spec, for example, I might call that a quality problem. But that's local to the group you're working with, is who then gets to work on that. Is that a manufacturing quality engineering challenge to go solve, or did it get to the field and cause problems going forward? So I don't know if there's a best distribution to recommend. I start with Weibull with time to failure data. I almost and it really depends on the failure mechanism, what I'm dealing with. And so I might use a normal distribution to start with stuff on a production line when I'm looking at those kind of things, but it's the nature of what's causing the failure. Is it variability in our process or variability in the material sets? And it can be, plus or minus a particular standard or specification. Then normal is probably where I would start. But like Weibull, it's just a starting point to where we want to go. Not useful for repaired systems, a question from Mark. What about the case when a bearing is replaced and the equipment may have some accessory components repaired or replaced? So Weibull, log normal, gamma, all these time to failure distributions are assuming that the unit is good as new when it starts and it continues in that realm, right? And once it's failed, it's out of service, it's gone. When you're looking at a system level where I'm replacing a bearing or I'm replacing a flange or I'm replacing a belt or I'm replacing, some component or I'm making adjustments to it as it's failing, like a car, if I change the timing or rotate the tires, I, do a mixture of preventative and corrective maintenance, the system is running at various stages of newness all the time. And so, and there's many competing failure mechanisms in the individual components. And so it's called renewal data when you're evaluating what's the effect of the repair processes. Is it making the system as good as new again? Or is it making as bad as old? I replaced just one bearing, but everything else has got 5 years of age on it. And I know in Weibull++ and in the literature, there's ways to do renewal processes where you don't have to go to those two extremes. You can go, it's after this sets of repairs we've done, it's 90% as good as new, right? And we can account for the types of failures that we're dealing with. And so if you just apply a Weibull distribution to it, one of its underlying assumptions is that the data is, once it fails, it's failed, it's out, it's gone, and it's replaced by something new, or another item is put back into the population. And it's appropriate, most appropriate when we're dealing with a single failure mechanism. So we often fudge that a little bit and use it at a system level, but things that we treat like or assume that it's not repairable. So when you're dealing with, say, a factory piece of equipment and we're clearing jams and replacing components on a regular basis just to keep it running, then a Weibull distribution at that stage is really not appropriate. It doesn't give us an adequate description of what's happening in the system as it gets repaired, because we're more interested in the rate of failure, of arrivals of these failure or maintenance actions. And renewal statistics is a whole other class of statistics that allow us to accurately analyze that. And Wayne Nelson's got a great book out on it that talks about renewal processes. And you can find a few other places too. Not sure if I've answered that question well enough or not, but I ran into that kind of the hard way. It's really not appropriate. You can get a calculation, but it doesn't give you the types of information you're really looking for. And it's part because of the underlying assumption that in Weibull and regression analysis, the unit isn't altered and put back into service. It's replaced with a new one. And then it starts at time zero on its own. It's independent. Whereas if I got a system that's being repaired, each repair has the very real possibility of affecting other elements of the system, increasing temperature, or increasing vibration, or reducing that in those kinds of ways. That's one way to think of it. Yeah, and so yeah, if you have this idea of Shrivastan is exactly right. If you've got time to failure data and a pretty specific failure mechanism, you're in good shape. Weibel's where I'd start. And it's qualified as, I don't worry about what it's called unless you can enlist a bunch of other people that call themselves quality people to help you go solve the problem. That's great. But if it's time to failure data and it's in the field and you got a common failure mechanism to it, well, then Weibel's just fine. You can call it a quality distribution if you want to, that's fine. And there a note on it. It's caused by variability in the process. Yeah, we get a lot of our failures are caused by variability in our process. That's a very common source of defects that get to the field and lead to failures. And it starts with that design for reliability stuff and understanding your process capabilities. So it's a good story there. I like that. All right, so I got one more question here. Yeah. Growth does allow for multiple failure modes and failure mechanisms, and it's appropriate. I tend to shy away from it because some of the underlying assumptions of a constant failure rate, unless you make a change to the product, and then the failure rate should change for an improvement, which is okay. It gives us a crude model for that. I much prefer the renewal models in order to analyze that. They're a little bit more tricky. You need some software to do it, but it sure allows you to get a better answer, in my mind, than the growth models. They do have their place, and a lot of times our limitations on data is so massive that we do have to make a lot of simplifying things. Right? Last one, real world relationships. And here I wanted to say physics of failure equations. And an Arrhenius equation really isn't a physics of failure model. It's a relationship for chemists that relates temperature to the reaction rate of a chemical process. Now, chemical processes involve crack propagation, embrittlement, wear, actually changing the material properties, diffusion. There's a wide range of things that chemistry actually has a play in. Now, one of the things I learned over the years about the Arrhenius equation is that it gets misused all the time. And one of the most common ways it gets misused is we use it to model things that have nothing to do with chemistry. Now, it's just an interesting formula, right? And it allows us to do acceleration factors and all this other stuff. And we can empirically, we can go measure a bunch of different temperatures and their response to what we're interested in, and we can fit this curve to it. It's actually a pretty general purpose curve. And that's fine if that's what you do. The problem is what I run into is somebody says, oh, we know it's temperature. We're going to use the Arrhenius equation with an activation energy of 0.7 because we have no idea what it is, and then drive on from that. Well, no, you need to stop and do that sensitivity analysis. Well, what if it's 7.5 or what if it's 3? And you'll get completely wildly different answers because the activation energy is so important to this formula. And so getting it right makes a difference. But it does, even Arrhenius, when he created this, was just an empirically derived. He was assuming that it was collisions and energy to cause molecules to change, to break off atoms or add connections, things like that. But it wasn't derived from the first principle. It was just a set of experiments with different temperatures and seeing how fast the process happened. And then he came up with this equation to describe it. Another part of the original paper includes the amount of concentration of reagents. So we've simplified it for most of our purposes just to the temperature term. And it is useful. There's no doubt about it. But it's been so prevalently misused because of the lack of understanding of how important that activation energy term is, the E sub A. Yep. And you're right, Gregory, it is used in materials engineering. And a lot of times material degradation is a chemical process, right? And there's that Arrhenius may be perfectly fine. But the limitation is that you really do need to know the activation energy, right? If you suspect it's a chemical process, you really, really need to know the activation energy. Go talk to a chemist, go do the experimentation to determine it. Assuming 0.9 or 0.7 or 0.2 or something like that is very dangerous. Now, if you find that if you put 0.2 or 0.7 and it doesn't change your answer that you're getting or the conclusion that you're making in the decision, well, then you're okay. But that I have found it to be so sensitive to, because it does have a massive effect on the ability to say it's going to be a slow or a fast reaction. The other pieces are kind of obvious from chemistry things, is it doesn't work across phase transitions and things like that. So it's part of it. But the idea here is that one quick note is, oops, I'm hitting the wrong button there. This temperature, it may not be the only important thing. What if it's thermal cycling that matters more? Well, then the Arrhenius equation really doesn't help all that much. It might be more in the number of cycles, in the range of those cycles. Now, some formulas include Arrhenius term and the thermal cycling term, but you really need to understand where and when does it apply, and it's not a carte blanche that anytime I deal with temperature that it's appropriate. I always question, why are we using the Arrhenius equation? How does that relate to the failure mechanism that we have in place? Now, the same set of questions and same set of challenges go for any of the physics of failure models or any of the acceleration factor models. Does this really apply into the failure mechanism that we're dealing with? And how do I show that to myself? How do I check the underlying assumptions to make sure that this is the right equation for what we're doing? All right. Just because you find a nice formula that deals with degradation of polyethylene, well, does that apply in the range that you're using it? Is it appropriate for the types of stresses that you're using, the type of additives and attachments and so on? So question, which is really my final point, is challenge your assumptions, right? Check them. All right. So I know I'm running a little bit long. I pushed myself here with 6 formulas. I could have stayed with 4, but when I thought through it, no, that didn't quite cover what we got going. I'll stay on the line if there's any questions or discussion. And I appreciate all of those of you that could attend, and appreciate the input through the questions tab. So hopefully it gave you a couple of ideas and things to think about in applying not just these 6 formulas, but any of the formulas we've got that we deal with. So, and as usual, any one of these 6 could be a webinar in and of themselves, and doing some case studies, stuff like that. That might be an idea for the future. So with that, I'll say thank you very much for attending, and I'll check questions tab. I see a couple of things in here, and then we'll go on from that and enjoy the rest of our Tuesdays. Oh, also, before I sign off, what do you think of the format and the slide deck and stuff? This is a different program. The PDF is in the handout section. I'll have it online also. Any comments on the format? I know I could have made the formulas a larger font, but I got those in the wrong place. So Srivistan, when there's no repair done at the component and only replacement done upon its failure in the field, the renewal is not applicable. Yeah, in that case, the way you described it, I would probably start with the Weibull analysis if it's just replaced, right? And the new item is starting at time 0. And the assumption, though, is that the environment in and around it, wherever that item is being placed, doesn't, because of its age, affect its performance. Think about it as changing out a motor. If the motor structure and what it's attached to and stuff over time increases in the amount of vibration and the lack of alignment that occurs, then that motor will probably fail quicker. So if the surrounding environment after the repair is reset to time zero, like the first unit that was there, then Weibel is okay. But if the surrounding environment and structure that it's attached to affects the rate of failure of the item, well, then it's not independent anymore. And so using a renewal process is more appropriate. All right. Yep, Gregory, all models are wrong. I think that was George Box that said that, but I may be wrong. I've used it probably and attributed it to the wrong person for years, but that's why I remember it. The Boltzmann constant is a constant. There's only one value for Boltzmann's constant. It's a universal constant, so it shouldn't be appropriate. The Arrhenius equation, if you can find a technical paper that has a very similar structure and the same material set, same, excuse me, failure mechanism or chemical reaction, that's great. Excuse me. The first time I did a life test that used the Arrhenius equation, I went over to the chemist in our organization and asked him, here's the oxidation process I think is occurring. He confirmed that and gave me an activation energy. He was able to run a set of experiments. It didn't take him very long, that would estimate the activation energy using a chemical engineering process or chemist's process. And then I used that in my acceleration factor. So I felt pretty confident about it. But looking it up in a book, they often say, well, it's somewhere between 0.7 and 0.9, or it's between 0.2 and 0.6. Well, that's a pretty broad range for this factor. So technical papers from your prior work, worst cases, you have to go do it experimentally yourself. Run enough different temperatures and monitor the rate of process change, the time to failure is essentially, and you can use it as a fitting parameter. Best is to understand the underlying chemistry and talk to a chemist. Be a way to do that. Let's see. Thank Nigel. Appreciate that. Have a great rest of your Tuesday. Thanks for attending. Slides are good. Thanks, Michael. I spent most of the weekend just trying to get the format close to what we had and clean and all the other stuff, font sizes, all that good stuff. So good to hear. Hopefully not too distracting. Very welcome. Thanks, Riva-san. Thanks for all the comments.